Today I wanted to talk about volumes. Sorry, I hadn't turned the microphone on. I want to say more about volumes because so far I've said very little about volumes. So all I said is, the definition of the volume is this somewhat trivial definition of the integral over the polytope of the identity function. And what that really means is basically that you do kind of Riemann sums. So you approximate with little parallelepipeds, basically, little cubes or whatever. And then the other thing that we proved is that one way to compute the volume is to compute the Ehrhart polynomial of a polytope, and then look at the leading coefficient, and that's the volume. Okay. But what that means clearly is that it should be harder to compute Ehrhart coefficients than Ehrhart polynomials than to compute volumes, because the Ehrhart polynomial includes the volume. Okay, and sometimes it happens that you can compute the volume even if the Ehrhart polynomial is too hard to compute. And so I just want to say a few things about volumes. Okay. I mean, let me ask you, how would you compute the volume of a polytope? Whatever that means. So you would triangulate and then figure out how to compute the volume of a simplex, and then you might or might not know what the volume of a simplex is. Okay, and that's basically what I want to start by discussing is how do you do that? Okay? It's good to know how to do that. And let's start by talking about volumes of pyramids. But you should realize that a simplex is an example of a pyramid. Okay, so what's the formula for the volume of a pyramid? So if you I'm sure at some point in your life you were very confused about this, because first you were taught that the area of a triangle is base times height over 2, and then you were told that the area of a pyramid is base times height over 3, and probably the first time that you learned this you were very confused about why the 2 became a 3. And what happens basically is that 3 becomes the dimension. So it's base times height over d, where d is the dimension. Okay. So let's say that this pyramid has base b and height h. Then the volume of the pyramid, the d-dimensional volume of the pyramid, is equal to the volume of the base, but that's a d minus 1 dimensional volume, multiplied by the height and divided by the dimension. So let's prove this. Oh, I wish that I had drawn this example ahead of, I had drawn this picture ahead of time, but okay, let me try. So maybe this is our base, okay? And then our height is like this. So this is the height. And then this is the pyramid. Okay. What are we going to do? What we're going to do is, I mean, by definition, the volume is the integral over this polytope, and what we're going to do is integrate over slices of the polytope, over vertical slices of the polytope. Okay. So, sorry, horizontal slices of the polytope. So let's take a horizontal slice. Okay. So that's going to look something like this. And then maybe let's say that the height of that slice is t. Okay? And the height of the whole polytope is h. Okay? So then what you'll realize is that this is just a scaled version of B, right? What scale? Well, it's according to the ratio between H and T. So this purple thing is, what is it? T over H. That's the scaling factor to get it from size H to size T times B, right? And so that means that the volume of my pyramid is going to be the integral over T ranging from 0 to H. Okay, my variable is T. And then what I have to integrate is the volume of the slice. Okay. Now, there's one thing that we know about volumes is what happens when you scale a polytope. If you scale by a factor of x, then the volume scales by x to the dimension. Why is that true? Because it's true for cubes, right? For cubes, the volume is just the product of the. It's just for cubes the volume is just the edge length to the dimension, and so that scales like t to the dimension. So that means that the volume of this times b is just going to be scaling the volume of b by this factor. Right. And now we can pull all the constants out. So this volume is a constant. H over d minus 1 is a constant. And so what I have is the integral from 0 to h of t to the d minus 1 dt. Okay, and we know what that is. That's just t to the d over d between h and 0. So that's h over d to the d. And then h over d divided by h over d, h to the d over h to the d minus 1 is just h. So we get the formula. So that's it. Any questions about it? It's a simple proof, but it's kind of satisfying. I like this proof. And of course, you've done this for three-dimensional things, and this is just the d-dimensional extension. Okay. Okay, so that's the first thing that I wanted to show. Then the next thing that I would like to show, corollary, is the following. What is the volume of a simplex? So let's take a simplex, and by moving the simplex around, we're going to assume that one of the vertices is the origin. Okay, so I just take that, whichever vertex I prefer, and just parallel translate to the origin, so that now my polytope is the convex hull of 0, and then I'm in d dimensions, so I need d plus 1 vertices. So this is a d simplex in Rd. Then you might know already that the volume of the simplex is the determinant of the matrix whose columns are these vectors, v1 up to vd. Except there's two things we have to do. One is divide by 1 over d factorial. And the other thing is that a determinant might be negative, and you don't want to have negative volumes, so you just take the absolute value of this thing. Okay? So that's the formula. Okay, so how do we prove this? Proof first. Let's do it for the easiest one. So So let's assume that our simplex is the origin, is the convex hull of the origin, and all the unit vectors. Okay. So what are we supposed to get there? Well, if you put the unit vectors into a matrix, then what you're going to get is exactly the identity matrix, which has determinant 1. So what we should have is that the volume of this thing is 1 over d factorial. Okay. Maybe let's call this p sub d to remember that it's the d-dimensional guy. Okay. Well, this isn't hard because you should note that we can construct p sub d recursively as the pyramid over p sub d minus 1, right? So these are 0, and the other, these are 0, and the first d minus 1 unit vectors, and then the last unit vector is going to be the apex of the pyramid. Okay. So this is the pyramid over p sub d minus 1. And so we can apply this formula, right, which says that the volume of my pyramid is equal to the volume of the previous pyramid times the height, but the height is just 1 because this is a unit vector, over d. Okay? And then you get it by induction, right? Because if by induction you assume that this is 1 over d minus 1 factorial, then when you divide by d, you get 1 over d factorial. Okay? So that means that this simplex does agree with this formula. Now, how do we do it for an arbitrary simplex? You guys have any ideas about how to do this? Basically, the point is that you can take any simplex, and through an affine transformation, you can take it to any other simplex. You just, or I mean, we can even say you can find a linear transformation that takes E1 to V1, E2 to V2, up to ED to VD. And that linear transformation is going to take this standard simplex into the simplex that we actually want. Okay? So we can do that. Let A be the linear transformation. So A goes from RD to RD. Be the linear transformation that takes the ith unit vector to the ith vertex of this polytope. Okay. Of course, what I'm doing here is what this linear transformation does is it just multiplies by this matrix. So A times anything, A of anything is just the multiplication by this matrix that I have here. Okay? And so then I can apply a change of variables to the integral that I'm trying to compute. Okay? So then what I say is that the volume of my polytope is the integral over the polytope of 1 dx. Okay? But then I do the change of variables given by the linear transformation. And so what I get is now the integral, instead of over p, I mean, again, the point is that A takes this kind of standard simplex into the simplex that we want. Okay, so So then a change of variables in the integral allows me to just integrate over this. Okay. But then you have to remember that when you do a change of variables in one of these multivariate integrals, then you have to multiply by the Jacobian, the determinant of the Jacobian. But in this case, this is just the transformation is just this linear function. And so the Jacobian is just this matrix. And so what you get is the determinant of A. Okay, this is the Jacobian. And so what you get is the determinant of A times the volume of PD, which is 1 over d factorial. Okay? So that's the proof. So that's good so far? Okay. So then you see that again, if you're able to triangulate a polytope, then that's a very useful tool, because if you want to find the volume of a d-dimensional polytope P, you triangulate P into simplices. Let's say T1 up to Tn, and then you just add up the volume of those simplices, right? Now you see that so far when we've tried to do this, we've been doing it for counting lattice points, and so we have to worry about overcounting. So are we overcounting here? Well, we're kind of overcounting, but we're just overcounting the boundaries of these simplices, okay? And the boundaries are lower dimensional, so they don't have any d-dimensional volume. Okay? So that means that I don't have to subtract any overcounting. It's just a straight up sum like this. And the point is that for each one of these simplices, I can just use that formula, and I'm done. Okay? So if your simplex is not too big, then you can triangulate it and do this. Okay, that works. Okay? And okay. So the next thing that I would like to do is talk about what happens when, one natural thing to do is to try to understand what happens with the volume when you do the different kind of polytope operations that we have. Okay? So for example, if you know the volume of P, and if you know the volume of Q, then what is the volume of P times Q? Well, it's basically volume of P times volume of Q, right? And if P is d-dimensional and Q is e-dimensional, then P times Q is d plus e-dimensional. And we're saying that that d plus e-dimensional volume is the product of the first d-dimensional volume and the second e-dimensional volume. Okay. So that's kind of trivial. I mean, it's useful, but there's not much to say about that. Another operation that we have talked about is the operation of taking Minkowski sums. And so what I want to talk about next is what happens when you try to compute the volume of a Minkowski sum. Okay. Because something really nice happens. So remember Minkowski sums. We said that if you have a polytope P, you have two polytopes A and B, let's say, then the Minkowski sum is obtained by looking at all the ways of taking a point in the first polytope and a point in the second polytope and adding them. Okay, so we discussed this already. And so let's talk about what happens when you do something like this. So for example, what is r times the square plus s times the isosceles triangle? The right isosceles triangle, so this is 0, 0, 0, 1, and 1, 0. Okay. So, I mean, of course, this is just some this is just a square of side length r plus the triangle of side length s. Okay. And then remember what you do. What you do is that so I had you guys do this with a concrete example, I think maybe even this example. So we said what you do is that you just take for each point in the left polytope, you put a copy of the right polytope. Okay, so maybe we do this. Okay, and then you start sliding it around until you get over here. Then you move it down until you go over here. And then you kind of move it back until you get over here, and you just kind of sweep the square with little triangles. Okay. And so what we get is something that is kind of like a mix of the shapes of the two polytopes. Okay. So here we get something like this is R, then maybe this is S. Okay. And then
you should have one of them where it's only meeting at the verge axis.
On
your purple triangle. So either at the top or at the bottom.
upper right corner. What did I do?
If you're extending further draw a triangle with that at the bottom left corner.
No, because I see what you're saying. Yeah. Thank you. Yeah, let's say that I started here, okay? And so I'm letting this be the lower left corner of the triangle, okay? So then I have to sweep that all the way around, and that means that I don't stop here. I keep going until I get to up here, and then like this. Yeah, thank you. Okay. And so you see what I get here is length R, then I'm calling this length S. I mean S root 2, but you understand that. Okay. Then I get a length R worth here. Okay. And so this is the object that I get. Okay. So what is the volume of that thing? So it's something like that. What you're doing basically is cutting it up into pieces in some natural way and then figuring out what the size of each piece is, right? So I'm guessing what you did is this. And then you said, okay, well, this is R squared. This is R times S. This is R times S. And this is S squared over 2. R squared plus S squared over 2 plus 2RS. Okay? Okay, that's fine. What I want to illustrate here is that when you do this, actually you get a nice full copy of the left polytope. Right? R squared is the volume of let me say R squared times the volume of the square, right? I mean that's where this R squared come from. It's just the volume of this thing, and you get this triangle that gives you this guy. Okay. And then the other thing is a little bit harder to interpret. Okay, it's not the volume of either the left or the right polytope, and we call it a mixed volume because it kind of measures how much the two polytopes mix. Okay. And so this is denoted volume, the mixed volume of the square and the triangle. Okay. This should motivate what I'm going to say next. Okay? Question?
So 2RS is the mixed volume?
No, the mixed volume is so this is the first volume, this is the second volume without the R's. So this is the first volume, this is the second volume, and then this is what I'm calling the mixed volume. Okay? What's the thing that I want you to get from this example? That if you fix the shapes of these two guys and you just scale them by different sizes, so if you let R and S vary, then you're going to get a formula that is a polynomial. It's a polynomial in R and S. Okay? And that's the nice fact that this always happens. So that's the next thing that I want to prove. Okay? Okay, you guys remember this? So I'm going to erase it, and let's state this theorem here that says that this happens in general. Okay. So theorem let's say that you take P and Q polytopes in RD, and you consider the volume of R times P plus S times Q. Okay. So the theorem is that this is a homogeneous polynomial of degree D in R and S. Okay. We're talking about D-dimensional volume here. So when I say homogeneous, what I mean is that this expression is not only a polynomial, but every single term has degree 2. Right? And that's what's going to happen in general, that every single term is going to have degree D. Okay? And so what we're going to do then is we're going to write this thing. I mean, if it's homogeneous of degree D in R and S, you only have two variables. So to make a monomial of degree D, the only thing you can do is have something like R to the I, S to the D minus I, right? Okay. So what I'm saying here is that this volume is a polynomial of this, and I just need to put some numbers here. And what I'm going to do is that I'm going to give these numbers a name. So it turns out that it's convenient to put a D choose I here, and then I'm going to write volume of P to the I, comma, Q to the D minus I. And then R to the I, S to the D minus I. Okay? But you should think that this thing that I have here is just some number, okay? And what I have here is what I call it the ith mixed volume of P and Q. Okay? So you see that these binomial coefficients and these things look just like the binomial theorem, right? So you can look at this expression and it almost looks like the binomial theorem. It almost says r squared plus s squared plus 2rs, except you need to scale the things a little bit. So the first coefficient you scale by this, the second coefficient you scale by this, and the intermediate coefficient you scale by this. But you keep the 2, which is that d choose I. It's just what you would see in Pascal's triangle. Okay. So that's the next theorem that I'd like to prove. That if you want to compute the volume of a Minkowski sum like this, then it comes down to finding this nice polynomial. Now, before I prove this, I need a nice lemma. So, I mean, let me tell you what the strategy is. So my idea is going to be to induct on the dimension. Okay? I'm going to induct on the dimension. And for that to work, what I need to know is how to go, because it's an expression about d-dimensional volumes, right? And so what I need is some kind of tool that allows me to go from d-1 dimensional volumes to d-dimensional volumes. That's what I'm going to need to make an induction like that work. Okay? And so that's the next proposition. To go from d-1 to d-dimensional volumes. Okay? So let P be a d polytope in Rd with facet description given by something like P is the x's in Rd such that ai dot x is less than or equal to bi for I equals 1 to n. Okay? So that's the inequality description of the polytope. And let's give a name to the facets. So let fi be the facet where ai dot x equals bi. Okay? So each inequality gives me a bounding facet of the polytope, and I give these facets these names. Okay? And actually remember that we already had a name for this, because this is the face of P that maximizes the linear function ai. Okay? Just to remind you of that notation. Then the volume of my polytope can be expressed as 1 over d times the sum from I equals 1 to n of these numbers bi times the volumes of the facets. Okay? So it's a nice recipe. It tells you just compute the volumes of the different facets, but then do something that's a little bit strange. Take each one of these things and multiply it by bi, which is the largest value of the linear function in that dimension. Okay? And the fact is that when you do that and you divide by d, you get the volume. Okay? So that's what I'm going to prove. That's a recursion that lets you compute d-dimensional volumes in terms of d minus 1-dimensional volumes. And if you're taking notes, then leave room for another statement that I'm going to put here. But we'll just see it come out of the proof. But this is right now the main statement that interests me. Okay. So how are we going to prove this? Actually, the proof is fairly simple. What I'm going to do is trying to think of how to draw this picture. This is the hardest thing. So I have a d-dimensional polytope. Okay. What I'm going to do is take a point inside, and then look at the pyramid from that point to every facet. Okay. So let's take a point in the interior of P. Okay. Let me try to draw a picture. Okay. I don't know how this is going to work out, but so I take a point in the interior, okay, and then I look at the cone to every face, to every facet. I'm sorry. Okay, so that's one. That's the cone for this facet. Then the cone for this facet is this one. And then, I don't know if you see them, but the other cones are immediately drawn in. For example, the cone for this facet is the only one that you can kind of see. And then the other ones are kind of behind. Okay. So this is Q. This is a facet. Let's say this is the facet Fi. So let's say that Pi is the convex hull of Fi and my interior point. Okay. But the point is that here's Fi, here's Q, okay, and what I have is a pyramid. So the idea for why I want to do this is that this is a subdivision of my polytope. And it's not a triangulation, but it is a subdivision. So I just have to add up the volumes of each one of these individual pieces. But the nice thing is that because each one of these is a pyramid, then I know how to do that, right? Because what I get is 1 over d times the base, right? But the base is just the facet times the height. We're going to have to do a bit of work to figure out what that height is, but whatever this height is. Okay. You think it's B? You think it's BI? It turns out that it's not, actually. That's what's nice about this proof. What is this length HI? Well, let me first ask you, what is this direction? It's the direction that maximizes this facet Fi, so this direction is the direction AI. Okay? And so it's along this direction that we're measuring. Now, the point is that what is the value of the linear function ai at this point? Let's give some names to things here. So let's say that this point here is t. Okay. So a sub I dot t is equal to what? Well, this is the facet. So this is equal to pi. Okay. What is a I dot q? We don't really know because q we just picked to be some random point. So it's equal to ai dot q. It's not very smart. So then, ai dot t minus q is equal to bi minus ai dot q. Okay, but the point is that t minus q is this segment that we're trying to find the length of. Okay. Now let me do something else. Let's assume that ai is a unit vector. Can we do that? We can by scaling. Yes. So why can I? Because I can scale by a number here and just scale bi by the same number. Okay. But we'll see that we need to do that. Okay. The reason then is that, well, this is a unit vector, okay? So when I take the dot product of this unit vector with a vector parallel to it, what I get is just the length of this guy, which is just hi. Okay. So this is hi. Okay. If ai was not a unit vector, then I would have to scale by some factor here. So that would break everything. But you see, hi is not bi like we might have guessed from the theorem. It's bi plus some other stuff. Okay. That's just what comes out. So hi is bi minus ai dot q. Okay. So let me separate this into two sums. The first one is this. And let's put the bi here. Okay, that's what I get from this. Minus sum from I equals 1 to n of 1 over d volume sub d minus 1 of fi ai dot q. Okay? And it kind of naturally comes out with a parenthesis here, because this is ai dot q. But what you should notice is that these things are all constants here, right? And here I'm taking a dot product, so I can move the parenthesis to here. Okay? So we're almost done, but we're not quite done. But this is what you should realize. So we got that the volume of P is equal to what we wanted plus some other stuff. Okay? But what about this other stuff? Well, this thing, we don't really know what it is, but it's some vector, I don't know, V. Is V a bad name, probably? No, we haven't used V yet. So the volume is equal to a number minus V dot Q. Okay? But this is true for any Q in the interior. And this is a constant, and this is a constant. And this is not a constant because it depends on Q. So what must happen is that this doesn't depend on Q. So V dot Q doesn't depend on Q. But that's kind of strange. What kind of dot product is this that doesn't depend on what you're dot producting with? Can you think of an explanation? The only way this could be is if V is 0. There's just no other way this could be. Now, this isn't true for all Q. It's true for Q in the interior of P. Okay? But if you're in the interior, that means that you can take a little ball around, and that means that this is true for a full dimensional worth of directions. So the only way this can be is if V is 0. So this can only be, this is only possible if V is the 0 vector. Maybe let me say it a little bit differently in case you're a little bit uncomfortable about this. Q is interior. Okay? So here's my polytope. Here's Q. And now let's take tiny vectors in all the unit directions. But make them tiny enough that they don't leave the polytope. Okay? So, I don't know. This is Q plus epsilon times E1, where E1 is a unit vector. So then we're saying V dot Q is equal to V dot Q plus epsilon E1. Okay, so cancel this, and we get that 0 is equal to V dot epsilon E1, but the epsilon is a constant. So we get that 0 is equal to V dot E1. Okay? So that means that V is perpendicular to E1. But I can do this for any hyperplane. So if you're perpendicular to E1 to E2 up to ED, you must be the 0 vector. Okay? So that's more convincing, maybe, than my hand waving before. And that does it, right? So V is 0. That means that this is 0 dot Q, which is 0. And so that means that our formula is true. Okay. This is equal to this. So that was our first goal, but then you see that for free we got a second statement, which is what I want to write. So my second statement is that summation from I equals 1 to n of d-dimensional volume of Fi dot Ai equals 0. No, this is not dot. This is not dot because this is a volume, it's a number. Right? So how should you interpret this statement? The AIs are the outer normals to the polytope, the unit outer normals. Okay? Now, because a polytope has at least d plus 1 facets, then you have d plus 1 vectors which must be dependent. There must be some linear relations between these outward vectors. And this is a beautiful one. It just says scale each one by the volume of the corresponding face, and you're going to get 0. And this is a nice statement that actually, I think even in the plane is kind of interesting. This would be a good exercise in plane geometry. So what am I saying? I'm saying that if I take these outer normals with length 1, Okay, and then I scale them by the length of the corresponding face. So I scale this to be of exactly this length. Okay, this is length L1, where this is length L1. Then I scale this by length L2. I scale this by length L3, and so on. So L1, A1, L2, A2, L3, A3, and so on. Then you get that these vectors add up to 0. I think that's a nice fact. It's not terribly hard, but it's a nice exercise in kind of plain geometry and a little bit of vector, a little bit of playing with vectors. Okay, I guess we're out of time. So this is going to be, we'll stop here. And next time what I'm going to do is use this proposition to prove this business about mixed volumes. And then I'll give you a very, very beautiful reason to care about mixed volumes. It turns out that mixed volumes appear in algebraic geometry in a really natural way. And I'll show you how that goes next time.